Okay, I wanted to go through some of the basics, and I chose several problems from the homework on elimination that I think represent what people may have been having more trouble with, or are just representative examples in general. So this one's not on the homework, but to lay the foundation, it helps to draw out all the atoms and all the lone pairs so you know where everything is. You can, do that a bunch of times and then you won't have to after a while, but what you're looking for is the base to remove one of the protons on the carbon adjacent to the carbon bearing the leaving group. There's our leaving group, easily spotted. This forms a bond here, kicks these electrons. They have to go somewhere, so they go here toward the pull of the electronegative atom. That's going to form the double bond here. It's going to kick off our leaving group with these electrons going there. You can keep track of formal charges and electrons all the way through. You create that double bond there, and that's one of the products. That's the product that can form from this. So another case that's real similar, look, everything's the same below here except that we have a poor leaving group. We can protonate that to make it a great leaving group, like we saw, I think, on that one exam problem. And our base can come in, pull that proton off, either one. These electrons kick over here to form a new double bond here, kick off the great leaving group with these two electrons, and we get actually the same alkene product from that. And if you want to keep track of charges and electrons, it generates water. So if you look at this middle structure here, that is virtually identical to what we see in problem A. And so it's really a matter of spotting the leaving group. Here's our water acting as base, pulling off one of these hydrogens, kicks these electrons over, kicks off the great leaving group, which ends up leaving as a neutral amine, and we get our double bond forming here, and so there it is. And this has no easy configuration, just like above, all the same ones above. Incidentally, this can only go via E2 because you cannot have this leaving group just leaving initially to create a positive charge there. That's a primary carbocation, which is impossible to form, basically. Now, the tricky part of this was recognizing that the right half of the molecule could also be basically a leaving group where any of these get plucked off, form a double bond, kick off the great leaving group in the other direction. You get this most simple alkene. So that was a good one. It was the most challenging one probably on the set to spot what was going on, but hopefully you see the analogy to the protonated alcohol above. Problem G had some good stuff in it. And again, spotting the leaving group, chlorine, that's easy. This can go via E2 or E1. I'm going to show you E2 just for speed, actually, in this case. You have your base. You can remove one of the adjacent protons here, create a double bond there, kick off the leaving group there, get your alkene. Again, no E or Z configuration there. In the second example, we pull off a different proton, also adjacent, kicking those electrons over. You get here, again, no easy configuration because you've got one carbon with two of the same group on it. Anytime you have one carbon of the alkene with two groups the same on it, there's no easy. And you can ponder that for a while, but basically it's because there's no difference if you flip it over. We have more hydrogens adjacent. On the other side, we can pull off one of these. Create a double bond there, kick the leaving group off there. Now we have E and Z configuration possible. So we have the double bond here. The way I like to remember it is you prioritize the groups on each carbon. This would be priority group 1 and 2, using the same rules as we do for chirality, actually. Priority group 1 and 2, and then you look from 1 to 1, it looks like a Z, so it's E. Now, why do you get also the Z forming in every case like this? because you have free rotation around this bond right up until the moment when this hydrogen is pulled off. So if that bond has rotated around the other way, you end up with the other isomer. So E and Z always form, really. They might form in different amounts, but in a case like this, both of them always form. Problem J. Whoops. Okay, problem J here. I'm going to show the E1 route, although this can go E2 as well. The E1 route involves dissociation, just like the first step of SN1 reactions. You get your carbocation, and in this case, it's a secondary carbocation. Point that out. Water can come along and remove either one of these adjacent protons to create the double bond. So it's a two-step version of the E2, but the arrows are the same, if you notice, as the E2. It just happens in two steps. You get an alkene here. Technically, it's a Z, but in rings, we don't usually bother to indicate that because they don't really have a choice. So alternatively, you can pull off one of these protons, kick electrons in, I'm sorry, back up a step. You pull off this proton, kick these electrons over here to create the double bond here again. And notice this is now trigonal planar, so there is no wedge shown. And people, a few people were making mistakes on that, showing wedges and hash marks on trigonal planar structures. Okay. Finally, some people recognize that this same carbocation intermediate in the E1 route, and here it is redrawn, can actually undergo what we call hydrogen migration. A pair of electrons that the hydrogen is attached with to that carbon can just pogo stick over, basically, to the adjacent plus charge. That's creating this new bond. And why would it do that? The driving force to create a tertiary carbocation from a secondary carbocation. So there's an energy gain there. Tertiary carbocations, as we know, are the most stable. Now, you can actually pull off adjacent protons in all directions and get the same product as we just saw above. But now you can also pull off one of these protons. These electrons go in and create this double bond here. And so you can get this possible product as well. So some people spotted that. All right, so I thought this covered a lot of ground. Notice how intrinsic structure and bonding principles are, geometry, formal charges, knowing where your atoms are that are implied, not always shown. It helps to draw them in. Your lone pairs. You really need to sit down and just work through this. It will get quicker the more of this you do. And notice the systematic and meaningful way that the arrows move, that to indicate movement of electrons. The arrows do not indicate lassoing of atoms and saying this atom goes here and this atom goes there. Okay, so we'll continue to work on this as we go.